It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee. Hi guys, welcome to one of my next videos. Today I'm going to be talking all about rate of reaction, and we're looking at what affects the rate of reaction and how we can use some graphs to represent that and explain it all in terms of what we call the collision theory. So what I want to talk about firstly is the collision theory, and basically in order for a reaction to occur between particles, they must do two things. Number one, they must have energy greater than or equal to the activation energy. Now, the activation energy is the minimum energy required for the reaction to occur. All reactions have a minimum energy, okay, and they must collide with the correct orientation. So what I mean by activation energy is if you think of one of our reaction pathway diagrams, so this is the reaction pathway along here, and here we have our energy. If you think about an exo or an endothermic reaction, so in this case I'm going to do a endothermic reaction. So we've got our reactants here, and then we have a graph that looks like this. So this is our products up here, this is our reactants down here. Okay, there's a difference in energy between them. All right, that's the enthalpy. Okay, the difference in the energy between the reactants and the products, in this case because it's a positive value, it's an endothermic reaction. And we have a distance here between the energy of the reactants and the top of our peak here. That's our activation energy called EA, and it's the minimum energy required for the reaction to occur. So that's the reason why we don't just have all these reactions occurring all the time around us. Okay, in order for them to, for particles when they actually want to react, they have to collide with the minimum energy required. So we can show the energy required and how many particles have that activation energy by using another graph. This one's called an energy profile graph. So down here we have energy, and along here we have the number of particles. Okay, and what we get is this bell curve distribution. Okay, so this is sort of the middle energy. This is our mean energy that all the particles have. We've got some that have lower energy, some that have higher energy, because you don't have particles all going around with just the same energy. Some are moving fast, some are moving slow at any given time. And what we're referring to by activation energy is this value here, and this is normally about any distribution, so there's our activation energy. And what that's telling us is that only these particles to the right, so this small number here, okay, only those ones have energy greater than or equal to the activation energy. So what that means is that only these ones, when they collide in the correct orientation, only those ones will have energy sufficient to react. So that in a nutshell, that's just the collision theory, and you need to be able to refer back to that and really have it in your head what it is. And we're going to look at different things that affect what we call the rate of reaction. Okay, so when we're talking about rate of reaction, it can be measured in two ways generally. It's either a change in concentration over time or a change in number of moles over time. And in reality, it's kind of the same thing, because if you change the number of moles, you change your concentration. Right? If your concentration changes, it's because your number of moles changes. Okay, so that's how we measure our rate of reaction. So first thing I'm going to talk about for rate of reaction is temperature. Okay, now when we're talking about these things, I want you to keep in mind, relating to the collision theory, four things. Okay, and that is what effect it has upon the energy of the particles, what effect it has upon the orientation of the particles, so that's the direction they're facing, whether they'll collide or not, what effect it has on the frequency of collisions between particles per unit time, and what effect, if any, it has on the activation energy. Those are the four things we want to consider whenever we look at any change that we're bringing in and seeing how that affects our rate of reaction. So, with temperature, okay, we're going to represent this by using the energy distribution graph that we just had before. So here's our energy along the bottom, number of particles here, and what we've got is our activation energy. Now, when we supply energy, so I'm just going to talk about temperature first in terms of increasing the temperature. So when we supply energy in the form of heat, we do a couple of things. Number one, we affect the energy of the particles. Okay, supplying heat gives the particles more energy, it causes them to move faster. Okay, so what that does is that increases the frequency of our collisions per unit time. Because they're zipping around faster, okay, we have a much higher rate of reaction per unit time. Okay, so demonstrate that a little bit using some marbles. Okay, so here we go. I've got some blue marbles here and I've got some red marbles. Okay, and at the moment you can see there's not much of a reaction occurring here. We haven't supplied any energy to the particles. Now, if I actually do supply some energy, and in this case I'm going to shake it, but imagine that we're supplying heat to it. Okay, you can see that what's actually happening is that we're getting a lot more collisions occurring. Particles moving around. Okay, they're colliding much more frequently. They have more energy when they collide as well. All right, so it's much more likely that when they do collide, they're going to have the energy greater than or equal to the activation energy. So we can represent that on this graph if we're looking at temperature. Okay, it affects the energy of the particles. So if we actually want to show that, we're going to draw a new graph here. Rather than our bell-shaped distribution here, if we increase the temperature, we're going to actually spread out the energy of our particles like that. Now what that's going to do is, rather than just this little small amount down here which we had, which are those that have energy greater than or equal to activation energy, what it actually does, it means we've now got all of these particles which have energy greater than or equal to the activation energy. So what that means is when they do collide, they're going to have the correct energy in order to react. And there's also going to be more collisions occurring per unit time, okay, because they're moving faster. Doesn't change our activation energy at all. Doesn't change the orientation of the particles. Just affects the energy of them and the frequency of collisions. So that's temperature. If we go on to the next one, and we want to look at the presence of light, okay, this is the second way that we can affect a reaction. Okay, presence of light basically does exactly the same thing as providing an increase in temperature. Okay. What it does is it affects the energy of the particles. We're supplying energy in, okay, and it also increases the frequency of collisions because we've got more energy of the particles. They're colliding more frequently, kind of exactly the same as temperature. So what we might want to do is think about what would actually happen if we had a reaction that was catalyzed by the presence of light. Okay, so think of photosynthesis, for example, where plants photosynthesize in the presence of sunlight. If you take a plant and you put it in a dark room, okay, what's going to happen? Well, if we go back to our energy distribution graph, okay, this is where we increased our temperature. However, if we were to, say, take away energy, so remove the presence of light, what would actually happen is our graph would look a little bit more like this. Okay? So what we're doing is we're removing the energy of the particles, so they would slow down. Okay? None of them in this case would have energy greater than or equal to the activation energy. Okay? So that would therefore mean that we're not having successful collisions with the minimum energy required, so the rate of reaction is greatly decreased. So that could be for a decrease in temperature, it could be removing light as well. This one here could be for an increase in temperature, the blue one, or it could be for putting more light into it, so flashing it with something. And if you think of old cameras with the negatives, they used to have open the shutter, let a small amount of light in, and it caused the silver to react and form a silver template, which was your photo. So one thing I didn't mention with temperature is that when we increase the temperature, the general convention is that a 10-degree increase, right, 10-degree rise in temperature is approximately equal to double the rate. Okay, so that's very, very important to remember. Okay, so it's when you get a graph of it, you don't get a straight line, you get like a nice curve, all right, which hopefully you've done in your practicals before. So presence of light, temperature, both very similar. Okay, supplying energy to the particles or taking energy away, it affects the frequency of your collisions per unit time and it affects the energy of the particles. Next one I want to talk about is concentration. Okay, concentration I'm going to show again by marbles. All right, but basically for concentration, what we affect again is the frequency of collisions. Okay, we don't affect the energy of the particles. Okay, because we're not changing the energy, we're not supplying any energy in. Okay, we don't affect the activation energy and we don't affect the orientation of the particles. So we're just looking at frequency of collisions, and hopefully we'll be able to see that best by actually looking at our marbles. So if I take out, all right, 5, 6 of the blue ones and 3, 6 of the red ones. So here we go. here we've got our marbles here. Okay, you can see if we just have it normal energy, all right, we get some reactions or some collisions between the red and the blue ones occurring. Okay, if we increase the concentration, so you put more particles in, and we'll just put more red ones in for the moment. Okay, increasing concentration of the red ones. What we're getting now, okay, same amount of movement as before, but we're getting more red particles colliding with the blue particles. Okay, if we increase the concentration of the blue particles as well, and we keep going with the normal energy, again we get more collisions per unit time. So increasing the concentration doesn't affect the energy, doesn't affect the activation energy. They still move with the same speed, okay? But because there's more of them, okay, we get more collisions occurring. This can also be represented by pressure. Okay, so if by pressure, when you increase the pressure of a substance, you actually increase the concentration. So if we increase the pressure and we take this container and we maybe double the pressure, so we actually halve the space that it's in. Okay, if we halve the space that it's in, hopefully you can see that as soon as they start moving, there's going to be much more collisions occurring. Okay, I liken this to driving dodgem cars, for example. So if you do it in a on a football field, very infrequently you're going to collide with people, even if you're deliberately aiming for them. Whereas you put everyone in a small little shoebox room, okay, in dodgem cars, going to collide all the time. So concentration only affects frequency of the collisions per unit time. Next one we're going to talk about is surface area. Sometimes you hear this called state of subdivision. Okay, so again I'm going to show this with my marbles. So I'm going to go back to my original container, and instead of the small ones, I'm going to use my big marbles. Okay, so we've got big marbles in here. Okay, as the particles move around, we get some collisions occurring. Okay, all right. But if we increase the surface area, and the way you can do that is by making smaller molecules. So let's say every one of these big ones is 2 small ones. So if we have 3 big ones, and we put in 6 small ones, same for the blues. Okay. Same surface area, all we've done is reduce the size of the particles, so we've got more particles in there. Same surface area as we had, increased surface area from what we originally had. Now, we get more red and blues colliding with each other, so we're more likely to have a collision with the correct orientation and the correct energy. So surface area has an impact again upon the frequency of collisions per unit time. Okay? It doesn't affect the energy of the particles, it doesn't affect the activation energy or the orientation. All it does is means you get more in there. So it's again a little bit like concentration. Okay, you're just creating more surfaces for them to be able to collide, which means more often you're going to get these frequent collisions occurring with the minimum activation energy, so you're going to have a successful reaction. Next one I'm going to look at is a catalyst. Okay, catalysts are a little bit different, and you have to know the definition of a catalyst. Okay, a catalyst does 2 things. Number one, it provides an alternate reaction pathway. Now, what we mean by that is rather than, say, going from A to B, okay, you go A into something in the middle and then to B. Okay. Now, the key for this is that there is a lower activation energy. Alright, so that's the first thing it does, provides an alternative reaction pathway with a lower activation energy. Second thing catalysts always do is they help to get the correct orientation. So what we mean by that is they help the particles to actually line up. So if you think about your fists, okay, if these are 2 particles and what you need for a reaction to occur is for your knuckles to actually interlock, like that, okay. Normally what you've got is, if you imagine these are particles, they just run flying around, and sometimes they'll collide into each other, and occasionally you'll get them hitting like that for a reaction, okay. What a catalyst does is it basically fixes one of them in position, for example, and gets them to actually collide like this far more often. Okay, So catalytic converters in cars are a really good example. You have a honeycomb structure which has a very high surface area that causes particles to stick to the surface of it, which means that when the other particles come in, they actually hit in the correct orientation straight away. So we can represent that a couple of ways. All right, and the first way to do it is with our reaction pathway diagram. Okay, so here we've got a reaction pathway diagram. This time I've chosen an exothermic reaction because our delta H is negative. Our reactants have a lower energy than our products. Now, what we've got here is our activation, difference between the reactants and the top of our peak. Okay, what happens when you actually do it with a catalyst? I'll go to a colour that's not there, I might choose orange, okay, is you lower the activation energy. So your reaction actually starts to look a little bit like that instead, okay. So your activation energy is now in here. So new activation energy, it's lower. So we don't require as much energy for the reaction to start, okay. We can also show that by using an energy distribution graph. Here's our distribution of particles, here's our activation energy. What happens when we bring a catalyst in is we actually lower the activation energy. So instead of being here, it comes lower down to here. Here's our new activation energy. And now what we can see is we've got all these particles here which have the minimum energy required to react. So it doesn't change the energy of the particles, but what it does do is lower the activation energy. So a catalyst, all right, lowers the activation energy. Very, very important. What it does also help with is the orientation of the particles. Okay? So the energy of the particles don't change, but the required energy to react does. That becomes lower, which is why activation energy is really important. It also helps to line particles up in the correct orientation to bring about a reaction. So catalysts are very, very important. It doesn't affect the number of collisions we have, okay? But it does affect these two. So you need to know that. Final one I'm going to look at is nature of the reactants. So what we mean by this is talking about what we're actually starting with, okay, our reactants. So easiest way to do it is just to look at two simple reactions. So if we have a precipitation reaction, for example, so if you have a look at, we're looking at silver ions and chlorine ions. So if you've got some chlorine in, so you say some dissolved sodium chloride, and you drop in some silver nitrate to it, straight away you get a very solid white precipitate of silver chloride. Now, what's happening here is that in your solutions you've got chlorine ions and there's some sodium ions in there, and you've got silver ions and there's also some nitrate ions in there. So you've got them in ion form. Straight away they'll come in and then bang, they'll combine and form silver chloride. So all you've got to do for this reaction is actually form this ionic bond. Okay? You don't need to break any bonds because that's, they're already broken in solution. So it's very, very quick for this reaction to occur. If you compare that versus a combustion reaction here, so we've got methane with oxygen gas giving us carbon dioxide and water. What you've got in order for this reaction to occur is you need to actually break these covalent bonds between the carbon and the hydrogens and between the oxygen and the oxygen, and then you need to reform the bonds between carbon and oxygen and hydrogen. Okay, so this is a much slower reaction because you've got to break bonds and then you've got to remake bonds. Okay, so this reaction is much slower than the initial precipitation reaction we just looked at because we don't have to break bonds. All we've got to do is form them in the precipitation, whereas here we've got to break and form. So nature of reactants can be important as well. So what you need to do is remember all those things that can affect the rate of a reaction. Okay, the nature of the reactants, catalysts, okay, surface area, presence of light, concentration, and temperature. That's the other one. Okay, not going to be able to fit them all on. So these are the 6 things that can affect the rate of a reaction. What you need to be able to do is explain them in terms of the collision theory, and when you're explaining those, okay, always keep in mind these 4 things. Okay, what effect does it have upon the energy of the particles? What effect does it have upon the orientation of the particles? What effect does it have upon the frequency of collisions per unit time and on the activation energy? Try and explain them using those graphs and you'll be fine. Hope this is helpful. Really encourage you to go back, have a look, go through each one. Okay? Any questions, just ask. Thanks, guys.